dramatic data shift. So the idea was that up until 2008, hospital was using a one type of medical record recording, right? Everything in the hospital is recorded in sort of this EMR, electronic medical records system. And before 2008, there was one medical record system. And after 2008, they switched to another medical record system. So every hospital, when it's time to change, switch, update, they rethink everything. And they say, well, maybe we could do things better and store the data better, which usually results in a lot of different fields. The data that was previously recorded is not being recorded. Now the data that's recorded could be related to the data that has been recorded before, but is called something else. So if you just assume that your data looks exactly the same and keep applying the same model, it just will not work, which is what is shown in the top left corner plot. Now, if you keep retraining the model every year, so in a year when there was such a shift, such a change in the system, then the model will not work. But if you are training on just the previous year, you would have it bounce back pretty quickly because it will be a new system, which is training on all new data. So that's better. The problem with that is that a lot of the diseases are actually seasonal. So flu is seasonal. There are a lot of inflammatory diseases. Allergies are seasonal. There are quite a few diseases that people are presented with at the hospital. They are seasonal. And so if that is the case, then if you're just training on the previous year, then you will see one instance, essentially, of that. So in November, you see so many flu cases. In the summer, there are probably basically 0 to a few flu cases. So you will see that seasonality pattern only once. And so it's not enough to actually account for that. And the data will be confounded. And the training, the algorithm will be not robust. So the idea that we proposed here, and this is published work we published last year in MLHC, which is published in Proceedings for the Machine Learning Research Journal, PMLR, is that clinical aggregations, and we tried all kinds of different aggregations, but clinical aggregations where the concept is meaningful clinically. And if you map all the data before and after to this clinical aggregation, then that definitely helps to recover against these sort of dramatic changes in the data. So that was the explanation. I'm not seeing the chat as I talk, but maybe Rodrigo can help me to monitor that a little bit. So the one that I haven't covered yet, and one that we recently started sort of analyzing, is the feedback loop. And that's something that, as far as I know, we've seen one paper that has looked into this issue, but it will become an issue. And I'll let you know what exactly I'm talking about. So this paper is also published this year in MLHC. Feedback loop is essentially the situation when a model uses labels that were influenced by itself. So this happens when a clinician decides to adopt decisions made by the model, but they are not accurate. They're just not, they have errors. So they are false positives, and the clinician accepts a decision made by the model, and that means that it's an error that the clinician would not necessarily make themselves if they had to analyze the data, now is making. So it's the system error, it's the model error that goes back into the label pool. And when that model is updated with this new information, now it's incorporating its own bias into the training. You see? So first model is updated using its erroneous labels. The model's own bias is reinforced, and so the model becomes worse over time. So this study that we have done is really more about showing how bad this problem is. And of course, in healthcare, we are not expecting to have perfect models. We are expecting models to be making errors a lot, right? Because of the context, because of all the other things that I have listed in the last hour. So if you think about if you think about an example, right? Consider an ML model that tries to predict death. So in this case, death is positive, life is negative, so binary classification. If the model predicts death, then the action in a hospital may be, so if the clinician says, okay, I think this person is likely to die, then we should move them to palliative care. Palliative care means end of life measures. So they stop trying to treat them to keep extending their life, but just to give them comfort measures for them to essentially die in peace, yeah, with least discomfort. So a false positive means of the system, it means that a patient could have lived if they were still treated, right? But the system says it's like the patient is likely to die, they are not treated, and they die. So with a feedback loop over time, the problem is that there will be more and more of these false positives. So this is just to show you that if the clinician gives blind trust, this is the blue curve, then the false positive rate over time from, say, 20% over time on that mimic data that I have shown before, it goes almost up to 60%, which is crazy. If the clinician says, well, I know this model is imperfect, I will trust it some of the time and not other time. And of course, clinician wouldn't just do it randomly. So they would have some kind of a strategy and use some of the clinical knowledge. So perhaps it would be more like an oracle. But to simulate, if the clinician trusts the model part of the time, then the false positive rate over time for the same model that it keeps updating and keeps learning will be not as bad as if clinician trusts the model completely, but it still deteriorates. So what we did was we tried to see what kind of mitigating strategies we could have. So we haven't solved this problem. We just showed that it exists, but we did try a few mitigating strategies, and there are lots of curves, and let me tell you what they are. So blue is the feedback oracle. This is as good as it gets, right? The blue is something that we know the exact label, so we keep feeding the same, the true label. Orange line here in the middle is if we drop false positives at random. So it's like conditional trust, but random conditional trust. The green is dropping all positive predictions. So in this case, we will remove from the labeling all predictions that are made by the system. So the system says not all prediction made by the system, but all positive predictions made by the system. So if the system says this person is likely to die, then that will not go back as a label into the system to be updated. The system will not see this. So this, as you can see, this green curve is the best strategy we have to be pretty much like the oracle. the other strategies don't work. So the purple is the worst, is when we just take all the feedback, and the red is feedback when we drop the low confidence predictions. And of course, low confidence predictions assumes that we actually trust the model, right? That our model is well calibrated, and sometimes you just don't have enough context, so your model is not as well calibrated as you expect. So these are some of the strategies that you could do right away, right now, if you wanted to implement a model in healthcare and wanted to try to mitigate the feedback loop. And then the question is, okay, well then should we update the model at all, right? And the reality is, because of the data shift, I showed a very drastic version of that, but there is a constant data shift. Something is constantly changing. Because there is a constant data shift, the reality is that over time, the model's performance does deteriorate. And actually, my understanding is that in the 80s and 90s, there was a big drive for using expert systems in healthcare. So this was like the early AI systems, and they were expert-based, so rule-based. A lot of them. And because they were never updated, they deteriorated to be, even if their performance originally was good, they deteriorated below being helpful. And so they just stopped being used altogether. And so now we had this AI winter when AI was not really used. But this is another point. I have to say that this is an open question in AI in general, I would say, but especially in healthcare, where it's really, really important to make sure that the system that I implemented, they keep being as good as you originally designed them, right? If they're not as good, then the clinicians have to know that. And of course, it becomes a chicken and egg problem. So this problem still needs to be solved. If anybody is interested, we are working on it continuously, trying to come up with solutions for solving this problem. So this is something that I wanted to finish and to tell you. I've already summarized what I talked about last time. I'm not going to waste time doing that. I think right now I will just go back to.
Connected to this, Anna, there is a question in the chat that says,
Yes,
humans might also make such false positive errors, so labels are noisy
absolutely.
in-house. Moreover, we can validate, yeah?
Absolutely. Sorry. Let me see
Yes,
the full
so yeah,
questions.
we can
Yes.
validate real data due to the absence of clear labels. There are classification techniques that work with noisy labels, such as positive on-label learning and mutual contamination. Have you considered these?
Um, so yes, some of this. It's a long question, so let me just start by answering. Humans do make errors, absolutely. And arguably, they make errors that a machine would never make, but machines make errors that humans would never make. So actually, a lot of published work shows that the system performs okay, the human performs okay, but together they perform better in terms of making clinical decisions and evaluating them. So that's the current strategy, I think, is to combine augmented health. But I would say that the sometimes the labels are not available, but what we ultimately have to do is we have to be able to evaluate and provide pretty concrete quantitative metrics for the doctor. So we started doing anomaly detection and things like that, especially particularly to address this absence of labels. But there are biases that that are in the labels that there is no way for us to account for. Like the systems learn high precision over things that are not very accurate. So Right now, these techniques, I think some of them that I know of, for the working with noisy labels, the positive unlabeled learning, we have a paper in review right now for unsupervised representation learning and things like that to avoid labels. You can't fully avoid labels because a lot of these labels are used in clinical practice, and that's how the doctors understand how good the system is. You see, so you will have to map to it, to the space that the clinicians are understanding, to get on the same level of reasoning with them. So it's actually it's hard, but yes, people are trying to use these techniques. So far, I think with variable success, and not in practice where the systems are being implemented, as far as I know.
So another popular question is in statistical testing in medicine, parametric or non-parametric models? What is your take between both?
Oh yes, so I saw some of these models on the Q&A listing, and the reality is that right now in medicine, there is quite a bit of a usage of parametric models, but also the questions that are being statistically evaluated in medicine are quite simple, right? It's not even whether, it's not predictive models. It's not it's whether a blood test is above a certain value or not, given all the blood tests that you have seen. So that makes sense to be treated in parametric fashion. However, in a clinical sort of analysis and the machine learning models that we are building, models tend to be not just complex, but also very, very highly dimensional. So there's a lot of non-parametrics that is becoming uh, standard, at least in the machine learning field. So I think sometimes when you can make a parametric assumption. Of course, it's easier to deal with, and if it's possible, I don't see a problem with doing that. But a lot of times, the distributions that you are trying to characterize are not high dimensional and highly non-Gaussian, and so there are no tests that you could use that are parametric to answer the question or reject the null hypothesis. So yeah, it's also quite interesting that I think statisticians and machine learners that approach healthcare problems think a bit differently about them. And instead of in machine learning, we think less about rejecting the null than prediction, right? We think more in terms of the prediction models, and those are just evaluated differently anyway. Yeah.
There's another question that I will reformulate it a bit. So the idea or the question is if there is work in machine learning focused on life elongation, on slowing down aging processes. Have you seen something
All
like
right. So in terms of the work in machine learning, there are several labs that are sort of dedicated to that. One is the Craig Venter Institute. I think that's one of the goals of the creation of that institute was for life uh, extension and longer life living. The Calico labs that Google owns also, that's their primary goal, is for life extension. And then there are various biological labs. So from my other hat, I used to do a lot more biological research. And in that space, caloric restriction in mice led to prolonged life in mice. We actually at some point looked at cell size as well. So depending on the cell size, which animals live longer or shorter, and whether that makes a difference. we didn't get sufficient um, sufficiently interesting findings in that space, but I think it was because we had too little data. I generally don't work on this problem. I'm sure there are a lot more labs that are sort of looking specifically at that. Again, people who are looking at mTOR pathway, a biological mTOR pathway, that's been associated with a particular drugs targeting that, and life extensions. But any drugs, they have a side effect. So depending on the quality of life you want to have for a long time, I think that problem is definitely not solved yet. I don't know if I'm helpful enough. This is again beyond the level, beyond the expertise that I have. It's not the area that I normally work in. So these are the places that I know. So maybe looking at the work that they've done, you'll find more research that's related to life extension.
Yes. And earlier today, you were asking us about so how the progress that we see in machine learning within the hospital, and apparently it's not that high. However, there are two questions that are connected. One is there is this famous quote by Jeffrey Hinton on saying that we should stop
Yeah,
training radiologists. Are we close
yeah.
from doing that? And related to this is how far are we from having AI augmented doctors?
So I think there was a discussion with Jeff about why he said what he said, because a lot of people got upset by what he said, predictably. And he sort of went back on that particular quote. He didn't mean it as in like uh, um, abolishing whole fields. But I think this is the field of radiology specifically that he was addressing. And my understanding is that a lot of the tools that are being produced are helpful to the radiologists, but could not replace radiologists yet. So we are not there yet, and particularly because of some of the machine learning challenges that I have outlined. Some of these models are over optimistic in how they evaluated things. Transitioning models or transfer learning between different hospitals has not been worked out properly yet. So if you train in one hospital and you don't have the data from another hospital where you're trying to implement the model, it usually, if you just try to implement it, it usually doesn't work. Um, and you can massage the model and the evaluation, and it will work eventually, but it there are no automatic cases that I know without a lot of work from both machine learners and clinicians that made such models work so easily. I have to say that simpler tests that don't do as well as some of the more complex machine learning models, they are more general. So they sort of work similarly in different models, like some of this statistical parametric tools. But again, they don't work as well. So the accuracy matters, of course.
So then, in your view, how far are we from having AI augmented doctors?
Um, so I think this was sort of um, uh, the poll, one of the poll questions that I asked the audience. I think within 5 to 10 years it'll be a lot more broad than now. There are some ethical questions that we are still trying to decide. In some cases, I think ethics is a big can of worms, right? And in some cases, human make very unethical decisions, and what do we do about that? But the reality is that every hospital and every senior management at the hospital will have to grapple with how comfortable they are in implementing this technology. And every hospital waits for their neighbor to implement something. And so again, it becomes sort of the catch-22 where um, until it reaches some sort of threshold, um, it will be very slow, right? The tipping point. If you guys read Malcolm Gladwell, the tipping point will have to be reached, and we are not close yet. So once that's reached, it'll become much more common. But as I said, I'm not in a rush because there are still quite a few machine learning questions that we need to solve well before it is implemented really broadly. Because I feel like there are a few scientists in the field who are taking this very, very, very seriously. But then there are a lot of companies that kind of sprouted up that are not as rigorous. And it really worries me because if their tools are being implemented, they don't publish how they do things, they don't publish their evaluations. And if those become implemented much more than the sort of the rigorous scientific approach, then I'm afraid that people will sort of some major mishap will happen, and it will be all over the news, and then hospitals will again become much more resistant to implementing it. Right now, they want to. They just are trying to manage the risk. If once the big mishap happens, one or two, it'll be harder. So I think we are trying to do as good of a job as we possibly can, so that whatever is implemented, we can sort of guarantee some efficacy, etc. But it is being used already. So there are AI tools. I know for a fact of several hospitals in the US that are augmenting care. I'm sure there are other places as well.
So connected to this, there is a question that says that we will be able to be much precise in quantifying survival or death probabilities. Are we going to face insurmountable ethical questions?
Insurmountable? Look,
Insurmountable.
I mean, humans invented ethics, right? We can invent the solution. This is not insurmountable. I don't think applies to ethics. This is it comes back to the ethics and philosophy, and ultimately there are solutions for everything, starting with the train tram paradox, right? All of this will just have to be translated into the legal framework, right? So what happens if something goes wrong? Who will be liable? And I think there will be a lot of discussion around that, but ultimately for now, it will be doctors. And so the doctors have to understand how to work with a tool effectively.
Mm-hmm. And when we're applying machine learning to healthcare,
I have a question. Sorry to interrupt you, Rodrigo. Can people turn on the cameras, please? Because I'm sort of talking into the void a little bit.
well, I have my camera on, so it is
Yes,
not a full void.
I can see you, Rodrigo. Thank you.
So when we're applying machine learning to healthcare, then we normally have multiple feedback loops because of the treatments and so on. So how does this work with the supervised setting, where we're assuming that we have a complete data set, but in reality, data is arriving over time? What you have seen, how can it be addressed?
That's a very good question. I think we've been sort of looking more and more at semi-supervised approaches and sort of hybrids, right? Unsupervised approaches where you can help by the label, using the labels, whatever labels that you have. And a lot of times we ask clinicians to label some of the data for us to start, or to just see how we are doing and whether it's useful to them what we are doing, if it's, say, unsupervised. But we are trying to work, at least in my lab, we are trying to address the problems less in a classification sense, but more in the anomaly detection sense. So establishing the person themselves as the baseline, and looking at the degeneration of the signal with respect to themselves. right? So the anomaly with respect to how they have performed in the past, how they have been in the past. So this is what we are trying to do. That's why a lot of the projects that I have are related to sort of analyzing or incorporating Fitbit data, where the signal is continuous, where I'm hoping that this will help us to establish that baseline for a patient.
And well, also related to this is, are there ideas that you consider underrated in machine learning for healthcare?
The underrated. So anomaly detection in particular, treating the models in the problems in healthcare as an anomaly detection, I don't see a lot of that. I see people still doing the standard classification. I think it's very wrong. And the reason why I think it's wrong is because what we often try to detect in healthcare is actually very rare. So sepsis is a very common question that people try to address. So death, right? We don't have 50% of the people at the hospital dying and 50% of the people walking, right?
Yes.
Depending on the unit, of course. If it's a very elderly population, maybe, but the reality is across the hospital, it's a very small percentage of the people actually experience highly adverse events, highly critical events. And so um, what we have, and I think that's how it is proper to formulate this problem, is to say we have an outlier, a set of outliers that we are trying to detect, and we have everything else, right? It's not healthy and sick. All of these people are sick at the hospital. Our negative sort of control cohort, they're not healthy. And because for healthy individuals, we would never have all these tests done, right? They're not at the hospital. We don't have their data. We have the data for the sick individuals that presented to the hospital for a different reason. And that's very different, right? So you have a very heterogeneous sort of one class, right? And an outlier. So I think it makes a lot more sense to treat these problems as anomaly detection problems, where you're maybe trying to learn a generative model for everybody but these outliers, and then use generative models to detect the outliers that you care about. This is what we are trying to do in several cases. This is one of the problems that I think is highly underrated and needs to be addressed. Also, one of the first questions about time series, I think there's not enough work in machine learning with time series. We have, 2, 3, 4 maybe classical deep learning models that are used to model time series in healthcare, and they're okay, but they're not great. And so I think this area in healthcare needs a lot more attention. There are people who have been publishing in this area, like Suchi Saria, that have been publishing in this area extensively, and Michaela van der Schar and several others, of course. But we need more people. We need more work in this area, just from the plain machine learning perspective, not even just health.
And so talking about current practices, p-values are pervasive, and we know that there are some limitations about them. So do you see them as going away as the standard? And if yes, to what they will be replaced for?
I think it's all related to the original question about statistical testing, right? Sometimes p-values are appropriate. They're not going away. I mean, this is a statistical tool that is appropriate in some context and not appropriate in other contexts. I think this is what I think will be interesting and that we will see more of is how do you evaluate something on a personal, really truly personal level, right? Because we currently AUC, AUPR, all of these are aggregated population measures, and what we need to know is for which kind of people can we make good predictions that we are confident with, and for which we can't. And honestly, there are not a lot of tools that are very good at that. So I think we are switching more to that, and there are this sort of chef values and things like that, studying which features are important, which individuals. This is becoming more interesting. P-values will be used, I hope, as appropriate in the specific tests that are being done. I don't think it's either or. I think all of these tools should be used in, in the appropriate context.
And when working with patients and in medical data, one has multiple sources. You described now, for example, Fitbit, sensors, and so on. So in your work, how do you deal with this myriad of sources?
So it depends. We have some work that specifically integrates heterogeneous sources. We created a similarity network fusion for that purpose, but it's more like a descriptive type of work. It's less predictive. There are quite a few tools right now that are fine with taking multiple sort of different types of features and aggregating them, and sources that are aggregating them. There are ensemble models. There are tools that do that. I don't think that there are yet particularly elegant solutions that are a staple in the field. Sort of everybody would do this. If you have a lot of heterogeneous resources, everybody would do this. With respect to patients, I mean, you hope that your model is expressive enough that will capture the heterogeneity. Of course, you have to worry about overfitting, but I'm sure people who are on this Zoom call all know about that.
Mm-hmm. And one of the questions is basically related to causal discovery. So in medicine, there are so many factors that can lead to a type of outcome or a disease. So where do you see here causal discovery playing a role? In which are exciting areas that you see here for causality?
Well, everything is exciting about causality. If it wasn't only that hard to do in, from observational data, right? Because in clinical care, you basically are collecting observational data and then try to infer causality, and that's really, really hard. I think so. The way that we've been using two things I want to say. One is that we had a study on suicidal ideation. This was trying to figure out when what are the factors that are leading to suicidal ideation. We tried to do causal modeling for that. And the reality is that we did both causal modeling and standard associative modeling with features. And in the end, when the clinicians saw the results, the psychiatrists that we've been working with, they said the associated features that we found that were not causal made more sense to them from clinical practice than from causality. And the reason, one of the reasons that we found was that the clinical data, of course, observational data is very imperfect. So you have to impute. And we showed basically in that paper, I think, I don't know if it was in one of the NeurIPS workshops, but it's what we found was that depending on the imputation, the causal structures change. So it's really the methods that we have been using, they're not really robust. I mean, it makes sense, right? If you suddenly have different values, then the causal implications would be different. So there's a lot of problem estimating causality from observational data, and a lot of the models that are out there that I really like from the theoretical perspective, they're not quite applicable to the real data that we have right now because of the assumptions that they make. So the way that we use some of the causality theory is sort of in a counterfactual inference. So we try to build generative models and we say, okay, if we were to, not see this event, we would predict that this would be the course of action, right? Based on our generative model. But now we saw this event. How different is it from what we would have expected? So in that sense, sort of building generative models and working with counterfactual inference is not uncommon. So we are doing it for explainability purposes. David Sontag has proposed and used it for treatment effect estimates. And there's quite a bit of work in sort of this area. Again, it's sometimes hard to evaluate, of course.
Mm-hmm. Mm-hmm.
But yes, I mean, great. Everybody wants causality. It's just, I would say that for practical purposes, it's really hard. Yeah, people are working on it.
And so talking a little bit about yourself, can you share some words in how it is that you end up where you're now? How it happened? Were there some events that brought you into healthcare and machine learning? Now it sounds like a very intuitive connection, but many years ago it was not that obvious.
I think when I was doing undergrad at the University of Louisville, of all places, I was working in an IT department as a programmer, and I had to develop some tools to collect data, like a lot of tools. It was a gas and electric company, and I was developing tools to help them store data. And I really wanted to analyze it, and they weren't doing it at all. And I was like, "What? This makes no sense. This is very interesting. What are the patterns in the data?" And they're not looking at it at all. So for my master's, I was looking for a program that was specifically geared to do. At that point, it was called data mining in 2000, 20 years ago. So this was sort of my first foray. I had some AI courses, and I thought it was more fun than some of the other courses, of course, in undergrad. But I thought this kind of the idea of building models to understand data better is something that was just a natural interest for me from the beginning. On top of the computer science, I mean, I was always interested in computer science.
Mm-hmm, mm-hmm.
But to end up in healthcare, so this is actually what happened after I finished my PhD. My PhD was in modeling, using graphical models to model social networks, and like very large social networks, millions of nodes. And I found that like interpretation is just a bit of a joke, right? So we used maybe IMDb, and we predicted which actors are going to play with which actors. And I was thinking there, and like, who cares, right? So I thought, okay, I can, maybe with what I know, I can actually make a difference in the world, right? Help people who can't do the work that I'm doing, but they could benefit from my work. And so for my postdoc, I was looking for areas where this could happen. So I did computational biology for my I did 2 postdocs actually. I did computational biology for both of my postdocs, and for a while I really enjoyed that. And I feel like I have some intuition that I have developed for biology, which is really helpful. But ultimately, I'm worried that it's actually very interesting that in biology they don't incorporate clinical data as much. So, like somebody pointed out, all the patients are different in a variety of ways, and that's presented in symptoms, right? They present very differently. We all staple that as one disease, right? We recognize this as one disease, but they look different. The symptomology is different, and so there is a lot of this heterogeneity. And ideally, I think we should have both biological and clinical data to combine to make inference. And right now in biology, they don't look at the phenotype because it's really hard to get clinical data. And they measure biological data on very few individuals. So I started sort of looking at analyzing clinical data, of which there is usually a lot, right? It's hospital records, it's tens of thousands of people. It's also more appropriate for machine learning design, the more classical machine learning design. And then slowly, I think the biological data will catch up, especially in cases where it's needed, from microbiome and environmental stuff. And we'll slowly start incorporating that. So that's my hope. I think that's where we'll go in healthcare eventually, once it becomes affordable.
Yes.
I think that engineering should play a bigger role than it's playing right now. Sort of bioengineering and electrical engineering, because mechanical engineering that's developing biofluidics, it's really, we need cheaper ways to get that data. And I feel like all of the technology and the robotics is there. We just need to put it together to make it happen. And then I think we'll have a lot better medicine. And then the doctors will be left in the dust, because it's impossible to analyze all of that data. This biological data is really, really hard. And it's a lot.
And in recent years, the field has grown massively, it has become very competitive. So which advice do you have for anyone trying to sharpen their profile, especially when applying for a PhD program or a postdoc? What would be your advice to stand out?
So to stand out, what matters in graduate school is papers. So papers, experience, everybody has undergrad with, good grades coming into top universities. This is, it's a must. It's a check mark. So you have to have it. But in addition, you have to have people who have papers out of undergrad. They're considered at a higher level, because this shows that they are able to produce scientific work, right? I mean, it's a lot of work, right? You have to write a good paper, you have to do good work, you have to write a good paper, you have to submit it. I was lucky to have been working with with a professor in my undergrad, with whom we published a couple of papers. Otherwise, it would have been very hard to get into a place like Carnegie Mellon or U of T, or other places, MIT. But I think this is one way. If you don't have papers, I suggest sort of experience, and if you are taking courses online, right? A lot of people are taking Coursera courses and all of this. This is good, but it's much more compelling if you do a project. Like if you take that knowledge and apply it to something real. There's a lot of public data that's available. There's a lot of that you can download. For healthcare, there's public health data, but there is also UK Biobank data. There's Mimic data. These things are publicly available repositories, and of course, not for healthcare, imaging, tons of data, but not just imaging. There is I think, there are lots of repositories of data, and just do a project. And the difference is that when you apply your knowledge, you'll see what the gaps are, and you'll be able to reason about machine learning in a much more mature fashion than if you just take a course, right? Because like I said, the way that we get taught machine learning, and I was taught, it's very nice, but it's almost too theoretical, right? It doesn't directly apply. When you start working, when you start developing your own models and methods, it's much more, you learn a lot more. Hands-on work beats it every time. And so and then you start developing your own questions, right? What do we do in grad school? Research is more about figuring out what gaps there are and how to fill those gaps, right? Or what are the new frontiers, and pushing in those directions. And I think from that perspective, it's really important to start developing that intuition. And to develop that, you have to start using the tools that you have to understand what the gaps are.
Yes, yes. Well, and it has been a very entertaining discussion, and we have covered many topics. And I hope that it was also very interesting for the audience. I'm sure about that. And finally, we are basically finishing, but there is a question on how can people contact you? Is it best per email, or do you have any preferred channel how someone can reach you?
So people can definitely send me an email. I can't promise that I'll respond to every email because I get a lot, and it sometimes just falls through the cracks. I don't even notice. Like sometimes I get a batch of 100 emails and I look through them, but it might drop. So there is a way if people are okay with their email not might not be answered, and don't take it personally, please. I think email is really the best way, and I suggest we try to keep our webpage, the lab webpage, Goldenberg Lab, up to date, so people can check other students that are working on particular areas and contact students directly, potentially, as well.
Mhm. Great. Well, Anna, thank you very much. It was a very nice two sessions with you, and now we learned a lot about this exciting field of healthcare, machine learning, and all adjacent areas. That is a very broad field, and we hope it was also entertaining for you.
Yes.
And that will be everything for this evening. Now we'll have our next session in about 8 minutes, and we wish you a very nice day. And likely you will hear from a couple of students who are keen on contacting you.
Okay, great. Thank you for inviting me.
Well,
Bye.
then, take care. Bye.
Bye.